Hey there folks, Kronos V2 here. Welcome to the third assembly language tutorial where I will be going over conditions, jumping and branching, and subroutines. So the first thing that I want to go over before we get to conditions is something called the finite state machine. In game design terms, most things that you'll be working with have specific states that they operate in. And the easiest way to figure out what we need to do for the design is to chart out how things are supposed to work. So in this particular example, as a hypothetical situation, we want to create a guard with a melee weapon. Guard will patrol until the C's player variable is set to true. Because this is just a hypothetical and just an example of how to make one of these charts, we're not going to go into any code here because, to be honest, like completely designing the AI for a guard would be a little bit much for this early of a tutorial. But when C's player is true, the guard starts to chase the player. When the guard gets within melee range of the player, it attacks. Immediately after the attack state, it recovers. And then if the guard loses sight of the player, it goes into a search state. So we begin mapping the FSM. So as said, we start out with a patrol state. Fairly simple, self-explanatory. You know, the guard just goes from point A to B to C, looking for the player. So the first thing is, while the guard is doing this patrol, we ask ourselves, can they see the player? If no, we go right back to patrolling. If yes, however, we begin chasing, which is the next state. During the chasing, if we continue to see the player, then we check to see if they're in range. If they are in range, we go into attack, then into recover, then back to chase. If we can't see the player anymore, if the player isn't in range, then we go back to chase. We move closer so that we can hit the player. If we don't see the player anymore, though, we go into the search state. If they find the player, they go back to chase. If they eventually run out of time and give up on finding the player, they end up back in patrol. As said, though, this is all hypothetical. Remember Metal Gear? When a guard found you, everyone just knew where you were until you moved enough screens or defeated enough guards. Realistically speaking, given the NES limitations, this is more likely what a guard's FSM would look like. Some pathfinding code would still be needed, but this is a whole lot faster and more akin to the original Metal Gear. So, why does the FSM matter? Why did I just spend all that time explaining how to make a chart? While I haven't shown any code, this is how you've got to think about logic for games. The action steps that you've already been working with are akin to states. They just have very specific triggers. For example, end of animation or end of a timer. If you followed the NESMaker adventure tutorial, the teleporting monster actually used a very simple finite state machine that didn't have any decisions to it. Appear, fire, disappear, move, then appear again, and the process repeats. Learning how to make finite state machine maps will make planning out your condition trees a whole lot easier down the line. So, in regard to conditions, when comparing numbers in binary, oftentimes you have to isolate the information you're looking for. For instance, if you were checking the gamepad input variable and saw that binary number, but only wanted the state of the last bit, you'd use AND to single out that last bit. If you want to turn on a specific bit, you wouldn't do this for the gamepad, mind you. You would use the inclusive OR command. If you wanted to compare two bits to see if they are not equal to each other, you would use the exclusive OR. The binary AND. When you need to check a small portion of a number, you use AND to single out the information you want. For each bit in a binary number, if the accumulator and the AND value are both 0, the result is 0. If the accumulator and the AND value is 1, the result is still 0. If 1 and 0, the result is still 0. And then lastly, if 1 and 1, the result is 1. Comparing each bit one by one is shown below. If the first 4 bits and the last 4 bits are different as in the first example, the end result is all zeros. The second set, though, ends up giving you the final binary number 0001, 0000, because the fourth bit, or fifth, depending on which direction you're reading from, is turned on. And so is that same bit in the other value. As an example, this is from the change to idle animation assembly file from the adventure module. All we care about is if a button is being pressed on the gamepad. If not, then we can switch to the idle animation. If so, then we branch. Next is the binary inclusive OR. OR is useful when you want to combine two numbers, preserving both. For instance, you've already used this if you've made your own custom HUD variables. You use ORA to turn on the individual bit that you want to check. Because if 0 and if both numbers you're checking are 0, the result is 0. If either of the numbers is a 1, you get a 1. If both are a 1, you get a 1. The example here is from Power Up Unlock Projectile. We want to turn on the second weapon. So we load up the weapons unlocked variable. We use ORA to take that second bit, starting from the right, mind you, and then we store it. Since one of the two numbers is a 1, that value is set to a 1. Next, we get to the binary exclusive OR. Exclusive OR, EOR, or more commonly known as XOR, is useful for inverting the value of bits in a value, or checking for inequality. For each binary, for each bit in a binary number, if both are 0, the result is 0. If either of them is a 1, if one is a 1 and the other is a 0, we return a 1. If both are a 1, we return a 0. An example of EOR I actually used in a piece of code that I was working on for my long health bar code. As it turns out, I didn't need it. There was a much more efficient way. But originally what I was going to do to see how much I needed to take from the second bar was do a subtraction. Load the number, subtract, and if it underflowed, find out how much it underflowed by, and take that off of the other variable. As it turns out, like I said, that was severely overcomplicating things, and I didn't have to do it that way. But here's the example of how that would work. Load the number 1. Set carry, because when you're subtracting, you need to have carry set. Subtract. And then really, if the number is negative, use the exclusive or FF to get the positive, or to get the inverse of the binary number, and then add 1, and you get how many you went over. So 1 minus 3 is 2 over. 2 under 0, really. So here are some things that you need to be careful when you're working on condition trees. If you want to check for multiple conditions, you typically need to do them in separate compare and branch blocks. Always check the options with the most requirements first. If you have any other checks that use the same requirements before it, the branch may never be triggered. As an example, if X, then action 1. If X and Y, then action 2. If X and Y and Z, then action 3. When we read that, it looks perfectly logical. Our brain thinks, yep, that makes sense. It should work. But when a computer looks at it, it's going to go, if X, yep, that's true, go to action 1. And because usually when you are checking things like that, you don't return afterward, you end up never executing action 2 or action 3. So the trick to solving that is do them backward. If X and Y and Z, then do action 3. If X and Y, then action 2. And if only X, then do action 1. Now action 3 will always be given a chance to run. If it doesn't need to run, then action 2 will have its chance. And then if it doesn't need to run, then action 1 will have its chance. You also need to look at ways to simplify the number of conditions that you're using. An example that I found someone trying to figure out was how to create different states for when they hit attack in the air. And they wanted to check, if attacking and in the air, if attacking and on the ground, if attacking and moving, etc. So I was actually thinking about this problem specifically to go over in the tutorial, and I realized it could be simplified very down to, well, technically 3 conditions. Well, 2 conditions. If attacking and if airborne. So, if when you hit attack, if airborne, then allow the attack to complete and play the airborne attack animation. If you're on the ground, as the person wanted, stop movement, do the attack, and do the ground attack animation. So this all comes back to the flowchart, the finite state machine. Using the example that I just went over, you can break it down like this. When you press attack, are they in the air? Yes. Do those. If not, go down the other branch. Doing that allows you to see every decision that you need to make, and you might be surprised at how much you can simplify your actions, your decisions. So next we move on to jumping and branching. Since we just got done doing binary operations, which are often used in conditions, it's only natural that the next thing to go into are the conditions themselves. Since 6502 assembly is not capable of object-oriented functions, code runs procedurally, always from one line to the next. That's why commands like jump and breach are important. Without them, no matter what your program state is, the program would always go down the same way, command by command. Line 1, line 2, line 3, 4, 5, 6, 7, 8, 9, etc. With jumping and branching, we can have logic that executes based off the results of a condition. So, line 4 could be if the player is pressing the attack button. And then if so, we jump to line 10. with branches and jumps, you go from a static program to a game. So how do we do this? First off, with the jump command. Since we've already covered branching in the previous episode, this is the next logical place to start. If you did the challenge that I presented last time, you will have actually gotten a brief look at this command. It's very simple. JMP followed by the label you want to jump to. So what would it be like without jump if we only had branches? Let's assume we have a piece of code that takes a number from the accumulator, then branches if the number is 0, 1, 2, 3, 4, or 5 or higher. We have a series of comparisons and branches. I've omitted some of them just because this block of code would have gone off the screen had I decided to put everything I actually wanted to fit in. So compare 5, jump to 5. Compare 4, jump to 4. Compare 3, jump to 3. The reason why I'm doing this is because if the number is 3, carry is going to be set for 4 and 5 as well. So you do highest number to lowest number. That way, when you check for things like carry, you jump at the first opportunity the carry is set. Continuing on, let's say that the result of that set of branches sets a value in memory, which we'll just call result for simplicity's sake. 1 loads 1, stores it in result. 2 loads 2, stores it in result, and so on. The value, I just realized I actually skipped ahead before I asked the question. Oh well, you probably already had a chance to read that. What would the value in result be if we branched to 2? Because of the fact that we didn't use any jump commands, the answer to that would be 5. But why is that? Why would it be 5? So, going through the code, we start out comparing to the number 5. The number's less than 5, so carry stays clear. Therefore, we don't need to branch. We compare to 4. Then we compare to 3. Then we compare to 2. Notice, carry is set now because that's the number we're comparing to. So, our branch takes us over to the other side of the screen here where 2 is. So then we load the number 2 into the accumulator. Technically it was already there, but for the sake of making sure everything is designed as it was intended, fill it in anyway, and store it in the result. But then we run into a problem. We move on to the next line. We're not jumping because the program counter just goes up by 1. So now we load 3, and we set it into the result. Then we load 4, and set it into the result. And then lastly, we load 5, and set it into the result. The jump command is good for handling branching cases like this, especially if we want to only run one case. By creating labels like a label like end numbers, after our conditions and inserting a few jump commands, we can change the flow of code. Here's the exact same code with the jump command inserted everywhere where it would be needed. So again, we're checking for the number 2. When we get to the number 2 in the comparison, we branch over to 2, the label. We load 2, we store it in result, but then we get to this jump command. And what does the jump command do? Sends us right to the end numbers. So now we get the expected result. So another useful feature of having jump is, remember that branch out of range problem that I talked about in the first episode where we were going over the processor? There's a simple solution. And the code to the right, compare 10, branch of carry is set to the maximum label, which, thank you, Google Sheets, for capitalizing that M. That would be an invalid label because the assembler is case sensitive. But let's just assume this would work for the sake of explanation. But let's say that in between that branch and the maximum label, it's too long, branch out of range. What do? We can't make it shorter. We need everything there. Reverse the condition. If you're checking for carry set, instead check for carry clear. Then add a jump for if the condition is true immediately after. Then last, put a label for the branch to jump to. We get this. Compare 10. Well, compare 1, 0, not 10. Bad habit of just reading numbers as numbers. But now, instead of checking for carry set, we check for carry clear. And if carry is clear, we jump to not maximum. If that condition is not true, so carry is set, we jump instead to maximum. It takes a little bit more space in the ROM, but it lets you make much bigger jumps. Lastly, we'll go over subroutines. They're an automated way of jumping to a location, then jumping back after a piece of code is finished. It can be used for functions that need to be used multiple times, but you don't want to bloat the code. If you've examined the NESMaker input scripts, you'd have noticed the RTS command at the end of each of those scripts. Those input scripts are an example of subroutines. So how does it work? First is the JSR command. The JSR command operates almost identically to a jump command, moving the program counter's pointer to the target address. The key difference is the value of the program counter is increased by 1 and stored in the stack before the jump. That way, the program knows where to go back when it's finished. It then jumps to the address represented by the subroutines label. Then when it encounters the RTS return from subroutine command, it pops that value off of the stack and jumps the program counter back to the location that it jumped from. Because JSR and RTS make use of the stack, if you try to utilize the stack, you need to make sure that you leave the stack in the same state that you encountered it. If you put a number on the stack and don't remove it, then when you use RTS, you're going to end up somewhere completely unexpected. So any changes you make to the stack need to be unmade, essentially. So that being completed, this is the second challenge. Earlier in the tutorial, I went over the AND, OR-A, and EOR commands. I want, in the new tutorial site that I have built, in the assembly simulator, I would like you to attempt this. A whole bunch of binary numbers, so I'm not going to read them out loud. Otherwise, we'd end up with, a minute or two of me just spouting out ones and zeros. But the result of AND should be stored in AND loc. The result of the OR should be stored in OR loc. And the result of the exclusive OR should be stored in XOR loc. Lastly, there will be code in the template that is deliberately there to scramble your results, to give you the wrong answers. Don't delete that code. Instead, I want you to jump over it. Now, I have actually gone, the first challenge that I wrote was honestly really poorly set up. I directed you to the Easy6502 website, well, GitHub page. I had the template on paste bin. It was a mess, and I know it. So I've actually come up with a much simpler solution. The simpler solution is if you go to kronosv2.github.io/nm6502, you can actually get to a mini site where, using the exact same assembly simulator, you can attempt these challenges with the templates already built in. It's a one-stop shop for basically everything you need to handle the challenge. And that's it for now. Next time, we will be going over some similar commands. For example, we've gone over increment and decrement. Store an accumulator, load from accumulator. There are some very similar commands that work on other registers. For example, load from X, load to Y, store from X, store from Y, etc. And also, we're going to cover bit shifting for basic multiplication and division. And with that, that concludes this second tutorial. I hope you have found it useful. If you have any comments or questions, please be sure to let me know. I will do everything in my power to address them. Anyway, have a fantastic day, and I hope to see you next time. Take care.